Hi everyone, I'm Joey Carlson and I'm with the Department of Electrical and Computer Engineering at UC San Diego. And today I'll be talking about our recent work on the analysis of dynamic metasurface antennas under matching network constraints, which was presented at the 2024 Asilomar Conference. So first we'll talk a little bit about the background and motivation behind this work. So we envision reconfigurable antennas as a key part of the next generation of MIMO. So a typical hybrid beamforming architecture that we show on the left has something like digital and analog signal processing for a hybrid architecture and then static antennas. So we do all of the different pre-coding and signal processing on with the digital and analog components. We envision something like a tri-hybrid architecture, where not only do we have digital and analog signal processing, but we have EM signal processing or EM precoding with reconfigurable antennas. So we have three different layers of signal processing as a part of our system to allow us to scale up the number of antennas and have lower power consumption compared to our traditional hybrid precoding architecture. So these reconfigurable antennas with our tri-hybrid beamforming architecture can offer that lower power, larger apertures. So then to create a reconfigurable aperture, we can sort of build it up from something like a static antenna. So with a static antenna and compare them. With the static antenna, we have naturally a very simple design, but it's not dynamic. We can't do beamforming with just a single antenna or multiple antennas, which then brings us to a phased subarray. If we attach a phase shifter in front of each of the different antennas, then we can control and configure each of the phase shifters to enable beamforming and then steer beam in a different direction. Which is great and allows us to do beamforming, but naturally the addition of power dividers, control the phase shifters and the control lines and everything, scaling up multiple antennas and phase shifters will lead to more components and harder and greater power consumption. Lastly, if we look towards a reconfigurable antenna, we can reduce the number of components significantly. By instead of using phase shifters for beamforming, we beamform with the antenna itself. The reconfigurable antenna has components integrated into it that allows for beamforming and steering a beam pattern. So this allows for fewer components and lower power. However, naturally, we lose a little bit of beamforming control by having reconfigurable components within the antenna instead of phase shifters. So now we talk a little bit about a specific type of reconfigurable antenna that we'll be discussing in this presentation called dynamic metasurface antennas. And we see these dynamic metasurface antennas, or DMAs, as a key antenna design for next generation MIMO communications. So what is a DMA? A DMA is a type of reconfigurable slotted waveguide antenna. So rather than having a feed into each antenna element, we have a single feed, which is the excitation of a waveguide, and then as power travels down the waveguide, it gets radiated out through different slots in the waveguide, which act as the antenna elements. So these slots that you see on the left are all the different antenna elements on the DMA, and then rather than having phase shifters connected to them, we have a reconfigurable component, which, as shown here, is a varactor diode to allow for beamforming with the different elements. And since varactor diodes and these other reconfigurable components are often low power or consume negligible power, DMAs can enable low power beamforming via these reconfigurable components like varactor diodes. Now, while dynamic metasurface antennas and reconfigurable antennas have a lot of potential benefits in terms of power consumption savings and hardware and cost savings, there are naturally going to be some limitations and challenges when compared with a traditional phased array. So for example, dynamic metasurface antennas as a type of slotted waveguide antenna have the fields within the waveguide actually affect the performance of the antenna and is something that you need to take into account when beamforming. So the waveguide propagation will introduce an inherent phase advance into the system and will also cause the fields to attenuate as power is radiated out. So both of these things are different from a typical phased array and need to be accounted for when beamforming with the DMA. Moreover, the tunable component of the DMA unfortunately leads to a limited weight distribution for the DMA. So we see on the right the figure on the right, an ideal phase shifter, which is unit amplitude and has a 360-degree phase range for beamforming, and then the DMA weight distribution, which is much more limited. It's called a Lorentzian constrained distribution, and as we see, we can only create weights in the lower half of the complex plane, so 0 to negative 180-degree phase range, and we have this coupled amplitude phase distribution, which also affects things, and so this limited beamforming capabilities naturally can lead to some beamforming degradation compared to phased arrays. Now, one convenient method of considering a DMA is to sort of think of it as a phased array, and so we make a comparison here for a DMA architecture against a phased array architecture. So with a phased array, we have a power divider or a splitter that splits the power of the signal evenly, and then we control our phase shifters there to do beamforming with the antenna, and the signal goes to the antenna. With the DMA architecture, however, this changes quite a bit. Because of the effects of the waveguide, we have that attenuation and inherent phase advance in the waveguide, which is shown there in the blue, and that gets cascaded onto each of the different elements there. So that's that cascading that we see in the blue. And naturally, most of the power is delivered to the first element, and then a little bit less to the next, and that's the whole point of the waveguide attenuation there. And then also the reconfigurable component allows us to control the amplitude and phase of the DMA element, which is what's shown in red there right before the antenna. So we have to control and deal with both of these different components for precoding, which makes it a decent amount different than a phased array. And so a lot of these algorithms for phased arrays do not map equally to DMAs due to these differences. Now, one of the key things that we want to look at is how we can maximize the gain for a DMA. And this is sort of motivated based on the link budget equation, where to maximize the received power of your signal when you send something out, there's all these different terms that are involved here, such as the gain from such as the losses from the transmitter, the transmit power, the propagation losses, the receive gain, and what we're looking at in our case, the transmit gain. And so the transmit gain for an antenna is typically dictated by a few different factors there, as we see, which are the two efficiency terms, the radiation efficiency and matching efficiency, and the antenna directivity itself. So the element radiation efficiency is based largely off of the ohmic and dielectric losses and radiation resistance of the antenna. So this is dictated by the design of the antenna. The antenna array directivity is dictated by the steering vector and array architecture, so how the antenna elements are spaced, where they're placed with each other. This will dictate what the directivity of the antenna is. The beamforming with DMAs has been a large subject of research in recent years to see some of these things like directivity. And then for our presentation, what we want to look at is matching efficiency with dynamic metasurface antennas. So how can we further increase the matching efficiency of DMAs such that we can continue to increase the array gain of our DMA? And this matching efficiency is largely determined by the source and the antenna impedances as well as the transmission line. So these will be some of the things that we'll be focusing on in our presentation today. Now, to further make a couple of points about the array processing of DMAs versus phased arrays, here there's a couple of examples of looking at the matching efficiency, radiation efficiency, and directivity of a phased array with an isotropic and dipole antenna, and then a DMA, which for reference here for the directivity, a DMA is a directional antenna. So for the matching efficiency and radiation efficiency, phased arrays using things like dipoles or patch antennas, or in this case showing the isotropic antenna, are pretty set in stone. They're generally very well matched and have good radiation efficiency, and there's some known parameters for the directivity, and we can calculate the broadside array directivity, assuming these lambda over 2 element spacing and 12 elements, as shown here. For the DMA, however, there's very, very little work regarding the matching efficiency for dynamic metasurface antennas. So it really has not been well studied what the matching efficiency is and how well matched DMAs are. Additionally, same with the radiation efficiency, there have not been very many studies, but there have been a couple people that have built prototypes and have done some measurements on the efficiency of the DMA. But for our paper, since we have not been able to find any work on this, we wanted to investigate the matching efficiency for DMAs and see how we can model and improve upon the matching efficiency for DMAs. So now we'll talk a little bit about the DMA impedance and beamforming model that we'll be using. So what we want to achieve, or what we want to learn more about for a dynamic metasurface antenna is, one, how can we model the reconfigurable impedance of a DMA? Since the DMA has reconfigurable elements, it is not actually clear how we should be modeling this impedance. And what kind of combination of lumped elements we might be able to use to model the DMA impedance. So even one question is just, how can we model a DMA impedance? And then the other one, once we've discovered how we can model the impedance, we want to see how we can improve upon the impedance. And moreover, we want to learn if we can increase the matching efficiency by optimally configuring the DMA weights. So since we have reconfigurable DMA elements, can we actually configure or leverage that fact, configure these different DMA elements to improve the matching efficiency? Those are some of the key questions that we want to answer in this presentation. So now a little bit about the prior work on impedance modeling for dynamic metasurface antennas that we can sort of build a base upon for our work here. So since dynamic metasurface antennas are a type of slotted waveguide antenna, it seems sensible to start at the prior work for slot antennas. And so a typical longitudinal slot antenna, which means a long slot in a waveguide, which is the most typical type of slotted waveguide antenna, can actually just be modeled as a very simple shunt admittance, as on a network. And then the waveguide in between it will act as some transmission lines, and so we can actually create the circuit model and impedance model for an entire slotted waveguide antenna based on many different shunt admittances with transmission lines in between them, where the transmission lines are dictated by the waveguide properties. And so it actually ends up being quite a simple way to do impedance matching with a slot antenna. And then as long as you design those different longitudinal slot elements to be well matched to the characteristic waveguide impedance, then you will have a high and good matching efficiency for your slotted waveguide antenna. Now, the one problem with this is that these shunt admittances are static, right? It is a static antenna, and so DMAs are reconfigurable. So then we can look towards matching networks for reconfigurable antennas for more inspiration on how we can potentially improve the impedance and model the reconfigurable impedance of the DMA element. So there's also been some prior work done on matching networks for reconfigurable antennas, and this often includes a reconfigurable matching network to better match that reconfigurable antenna load with a reconfigurable source. But one key thing here is that many of these reconfigurable antennas have their own independent feed, whereas DMAs have a single feed for all of the different elements. So while this reconfigurable matching network technique might work for these reconfigurable antennas, it may not be applicable to the DMA because of the specific waveguide architecture. So we need to combine these and come up with a new solution for matching with DMAs. We'll now discuss a little bit about the beamforming and waveguide model for the DMA. So the DMA weights are largely dictated by the polarizability model for a DMA. So DMA elements are often modeled as magnetic dipoles due to their subwavelength size and resonant nature with magnetic surface currents, and so we can model them as magnetic dipoles. And so we can show on the left the polarizability of a dynamic metasurface antenna plotted across multiple different varactor diode values, which is that reconfigurable component. And so as we vary that reconfigurable component, we actually move the resonant frequency of the DMA. And that tunability is what enables us to do beamforming. These different parameters for the magnetic polarizability equation are dictated by the DMA element design as seen in the bottom left there. So how we design the DMA element and what tunable component we choose will dictate how those curves look. and the DMA polarizability. Now to transfer this to your antenna weights and your effective antenna weight, it turns out when you tune your resonant frequency at a specific frequency, you'll end up filling up this Lorentzian constrained weight equation, which is what we see to the right of that. So by obtaining this polarizability model and having our tunable resonant frequency, we can create our effective DMA weights based on this Lorentzian constraint model, as we see here. So that is how we can model our effective DMA weights. And moreover, to model our waveguide, to model the DMA waveguide, we can simply model it as that inherent phase advance due to the waveguide phase constant, as we see there. And then we can also include that waveguide attenuation constant, which occurs due to the power being radiated out per element, as seen there, as well as an attenuation of the antenna weights. So we'll now talk a little bit about the isolated DMA element impedance model. And so it turns out that a single DMA element, making some similarities here to what's called a transverse slot antenna element, can actually be modeled simply as a series impedance lumped element. So it's actually quite simple to model the impedance of a single DMA element. It's simply a series impedance element in the same way that that longitudinal slot was a shunt admittance. And moreover, to calculate what the series impedance element should be, we can obtain that very easily based on the scattering parameters of the DMA element as seen in that equation in the middle. If we can obtain the reflection coefficient for the DMA based on simulations or models, then we can very easily obtain the reconfigurable lumped element impedance based on that tunable component as well. Moreover, we can model the waveguide as an effective transmission line with electrical length dictated by beta d, which is the propagation constant times the element spacing. So the waveguide is also very simple to model as well. It's just a transmission line with a specific electrical length dictated by the waveguide itself. Next, given this isolated DMA element impedance model, we can then calculate the total impedance for the DMA and then the subsequent matching efficiency for the DMA. So in the top left there is a recursive formula that we can use to calculate the total impedance at each DMA element. And as you'll see, it's a function of the isolated DMA element impedance at a certain element, and then the impedance at the previous element. So that's why it's a recursive formula. Given that DMA equivalent circuit model on the right and that transmission line circuit model, we can start at the element furthest to the right, calculate the impedance, and recursively continue to calculate the impedance at each element until we arrive at the last element, which will dictate our total final input impedance. Yes, and so it's a function of the isolated element impedance and then the waveguide as the transmission line transforms the impedance of the previous element, as we see there. So once we calculate the final input impedance of the DMA, we can then, it's very simple using just your basic network theory to calculate the reflection coefficient and then the subsequent matching efficiency of the DMA. So if we use this recursive formula to get the input impedance of the DMA, then we can very easily calculate the matching efficiency. And since we have the isolated impedance of each DMA element and that is reconfigurable, for any configuration of DMA weights for the whole array, we should be able to calculate a matching efficiency for the DMA. So now comes our proposed approach to improve upon the matching efficiency for a DMA. So our goal in this method is to improve the matching efficiency for a DMA when a beam is steered at a particular direction. So first we need to talk about how we can steer a beam in a direction. One very simple way to steer a beam pattern is to take your desired solution, which is your phased array solution, as seen on the right there, and then map it onto our Lorentzian constrained weights for the DMA, as also seen via that brown arrow there. So we take our phased array solution and simply map it onto the DMA weights, and that is in the equation in the upper left. What we looked at in one of our prior works is a way to improve upon this by adding in a phase rotation to the desired weights, since the unit amplitude weights will not change, since the beam pattern for the unit amplitude weights will not change when a common phase rotation is applied to all of those weights. However, when we apply a phase rotation to all of these unit amplitude weights, the mapping onto the Lorentzian constrained weights will change, and that will give us a new configuration of weights that might be better matched to the waveguide characteristic impedance, which is the motivation behind doing this approach here. So by adding in this phase rotation, we can still steer a beam in a desired direction, but we can potentially improve the matching efficiency. So we outline our matching optimization design procedure there, where we calculate our DMA weights based on our desired weights and that common phase rotation. We then use the equation seen in the previous slide to recursively calculate our input impedance for the DMA, given these configuration of weights and configuration of impedances. And then we simply calculate the reflection coefficient and then the matching efficiency, or in this case, the return loss, to maximize the matching efficiency and come up with that phase rotation that optimizes the matching efficiency. So then we can see some preliminary results on a design that we had worked on in a previous paper referenced below there. So we took this DMA design in HFSS with 12 elements and a spacing of 6 millimeters at 15 gigahertz, and tried to steer a beam at broadside at different weight phase rotations for that common phase rotation. So first on the left, we can see the DMA weights that we were able to achieve in the simulations to use for beamforming, and we see that it matches up very, very well with the Lorentzian constraint as expected. And then, given these sets of weights and simulations, we can calculate and do simulations for the return loss of the DMA across those different common phase weight rotations. And we can see how the return loss varies across the weight phase rotations. And we see that while it varies quite a bit, all of the different configurations remain below negative 14 dB return loss, which is already quite low. So it turns out the antenna is already very well matched to the characteristic impedance of the waveguide. And we can see that some examples of the calculated weights that maximized and minimized the return loss there. Just as an example to see how that phase rotation applies and configures and comes up with a new configuration of DMA weights. Lastly, on the bottom, we can look at the realized gain for the DMA in the pattern simulations. And we can see in both cases, for the case that maximized and minimized return loss, that we are still able to steer a beam at broadside, but there's about a 1 dB-ish difference in the realized gain for the case that minimized the return loss versus maximized. So we do see that the weight phase rotation optimization procedure did help to improve the realized gain, but not by necessarily a significant amount. So then lastly, we want to adjust our DMA design to actually have properties that may be able to better leverage our optimization procedure via the coupling factor. So the coupling factor for DMA is that term F in the magnetic polarizability equation, and it really determines the impact of scattering and the amount of scattering within the waveguide for a DMA element. So we can see on the figure on the left there, we have the element scattering as a function for two different coupling factors, low and high, and we can see that the reflection coefficient for high coupling is high. We get a lot scattered back, there's a lot of scattering, and for the low coupling factor, we have a lower amount of scattering. So really this coupling factor is an important parameter that dictates the resonant response of the DMA element and the amount of scattering that will occur when the waveguide fields come upon the DMA element. And this coupling can be impacted by the waveguide design, the offset of the element, and some things in the DMA element geometry. So there's a lot of different parameters in the design that can impact this coupling factor. And then we want to see how the coupling factor might impact the resulting impedance matching optimization procedure. We want to see if we can get a better impedance match or have better improvements for our DMA design with maybe higher coupling. It's also important to note here that While we discussed the series impedance model before, the series impedance model for the DMA actually is an approximation of the more general T-network model, and it begins to break down a little bit as the coupling factor increases, and so we'll be working with the more general T-network model to calculate the return loss and matching efficiency in the next slide. So then lastly, we adjusted that DMA design that we had shown before to have a higher coupling factor by decreasing the waveguide height, as we see there in the bottom left. So now with the lower waveguide height, we will have higher coupling, and we want to see how that impacts the matching efficiency of the DMA. So now we show both the return loss and the matching efficiency, again, as a function of that weight phase rotation. And now we find that the matching efficiency optimization procedure can provide some very significant gains to our matching efficiency and our realized gain, as shown in that plot in the upper right. We see that at 1 weight phase rotation, the matching efficiency is almost at 70%, while for another one, it goes up to almost 100%. So there's around a 25-ish% difference in the matching efficiency between two different weight phase rotations, or two different configuration of weights that point a beam in the same direction, which is significant. Just by optimally configuring the weights, we're able to significantly increase the matching efficiency. Moreover, as we see in the realized gain there on the right, both configurations of weights steer a beam at broadside, but there's around a 3.5 dB difference in that realized gain, which is a very significant amount of realized gain. And so simply by optimally configuring the DMA weights without any external hardware or anything, we were able to have significant matching efficiency increase and realized gain increase for our beamforming. So now we'll have some concluding remarks. So in this presentation, we found that DMA designs with low coupling factors are actually already quite well matched to the characteristic impedance of the waveguide and have a pretty high matching efficiency that may not necessarily need to be optimized. However, if we have a DMA design with a higher coupling factor, our proposed weight phase rotation optimization procedure can provide some significant benefits and improvement on the matching efficiency. And so in future work, we hope to extend this analysis and optimization procedure by doing a joint beamforming gain and matching efficiency optimization, and then test our proposed optimization algorithm with a fabricated DMA prototype. Thank you so much for listening to my talk, and for more information, please refer to the full paper. Thank you.